the third section in this lecture 2 will be the thermal migration. Based on this term, you know this mass transport or this atomic migration is due to the thermal gradient. So in the beginning, we are going to give you some physical concepts about what's the thermal migration. And next, we are going to show you how to quantitatively calculate the effect of thermal migration. What's the mass transport under this thermal gradient you apply on these materials. And also, in the electron migration, there's a beta, the value of beta or the sign of beta to indicate the moving direction, the direction of moving species, right? And here we also have we call it as a heat of transport to give you some information about the direction of moving or diffusing species affected by this temperature gradient. And next, at the end of these sections, we are going to give you some examples, really some kind of case study, and it will be the vacancy-mediated thermal migration case. The case of this vacancy-mediated thermal migration. Okay, so let's move to the thermal migration. So thermal migration actually is a mass transport under temperature gradient. So before we move to the definition, so I will give you an example about the thermal migration, where and how it happens. This is the gray slab, metal slab actually present is the silicon chip. So this is what we always observe is in the semiconductor is the silicon chip. So usually people will put the transistor or other microelectronics on this silicon chip side, and in order to lead all the signals or electrons out, people usually will bind this copper substrate to the silicon chip by this solder bond. And as you know, the copper substrate, the thermal conductivity of the copper substrate is pretty good. So usually this substrate also help benefit for heat dissipation. And as we know, the line width of the connecting line on the silicon chip usually is very thin, right? Because in order to get the smaller size of the microchip, the length is very small on the silicon chip side. In order to have in order to improve the heat dissipation, the connecting line on the copper substrate usually is very thick. The size is larger, and it will help the heat dissipation. And due to the diameter of the connecting line between the silicon chip side and the copper substrate side are different. So even at the same same amount of current density, due to the size of the conducting line is different. So you can expect, due to the jaw heating, you know the current density at the silicon chip side will be higher than that on the copper substrate side, right? Because current density here is higher than here, so there's more heat be generated at the silicon chip side than that at the copper substrate side. So that will cause a temperature gradient between these two be applied on this solder bond. So the red represent usually in order to drive the transistor or electron device on the silicon chip, usually we will apply a current passing through this solder bump and achieve or arrive the microelectronics, then lead the electrons out back to the copper substrate. Okay, so in order to demonstrate there's exists a thermal migration, so some scientists will do one thing. They will put the other number 3 and number 4 solder bump here, but there's no current passing through these two solder bump. But this solder bump do suffer the temperature gradient due to they share the same silicon chip, silicon substrate, and also the copper substrate. And let's try to enlarge one of this solder bump to here. So on the top, as we mentioned, due to the Joule heating, the current density at the passing through the conducting line on the silicon substrate is higher than that on the copper substrate. So that will result in a higher temperature at the silicon substrate than on the copper substrate, or cause a temperature gradient. And if you take a look on the composition, chemical composition of this solder bump is interesting. On the bottom part, you can, or the majority composition will be the lead tin alloy, and the bottom part, the darker gray region, is we call the 37 lead and 63 tin of lead tin alloy. And this is interesting because this composition is, if you take the phase diagram of this binary, or if you take this binary diagram, you can know this composition actually is at the eutectic point. At the eutectic point means that the melting point of this alloy is the lowest melting point at this composition, right? Lowest melting point. But upper part actually is a lead-rich region. And lead actually has a higher melting point. So this kind of combination is in order to what? In order to have a lower fabrication temperature doing to fabricate this solder bump, but this solder bump finally will sustain higher working temperature. So the upper region is designed for lead-rich region, can sustain higher working temperature. So this is how people deal and design this kind of geometry or composition distribution of this lead tin alloy. Okay, so now there's no current passing through this solder bump. Just this solder bump just suffer the temperature gradient. And before we this solder bump subjected to this temperature gradient, and the scientists analyze the element distribution on this solder bump. So as you expected, the bottom region, they use the SEM and use the backscattering electron mode to investigate the tin and lead distribution within this solder bump. And as expected, the tin majorly located at the bottom region of the solder bump, and the upper region is lead rich. But after applying this temperature gradient, after a longer period, then you can observe the lead moves from the bottom region toward to upper region. So this is evidence showing that there exists a thermal migration. That means this thermal gradient drives the mass transport of tin, and in this case is against the temperature gradient. The tin is pushed or moves from low temperature region toward to high temperature temperature regime, which will mean we is against the temperature gradient, right? So this is evidence showing that there exists the thermal migration. Okay, so thermal migration means that thermal gradient induced the mass transport, resulting from what? A closer effect between the diffusion species and the heat flow. And in this case, is what we learn, right? You can observe the mass transport due to the temperature gradient. So this must have a closer effect between this thing and the heat flow. In order to quantitatively understand the effect of thermal migration, so we need to do some calculations. So the materials now we have is you consider a dilute solution of interstitial component 1 under the thermal gradient. So we have a material, and we talk about the mass transport species are located at the interstitial site and with a dilute concentration. And we just stop dilute. Okay, so you can simply, because there's two possible driving force. The first driving force will be the temperature gradient, and the second possible driving force will be the concentration gradient, or you call it a chemical potential gradient. So you can, based on these two possible driving forces, you can formulate the heat flux J capital Q, and the interstitial atomic flux will be Ji or J1, right? So the heat flux can be based on the Fourier's law. You can write down as a minus kappa temperature gradient. Or some people want to write down as J capital Q is directly driven by temperature gradient will be the minus temperature gradient divided by T times the LQQ, capital QQ, plus the chemical potential minus chemical potential gradient times the coupling term. But it will finally will lead to equals to minus kappa temperature gradient, right? Because of Fourier's law. And if I want you to write down the interstitial atomic flux, definitely you can know the atomic flux will be directly driven by the minus chemical potential gradient times the direct coefficient. And the other driving force will be the minus temperature gradient, the over T is and times the coupling coefficient here, right? This way, actually, we are not interested here about the heat flow, because we are more interested in the mass transport under temperature gradient. So we want to know what's the J1 or atomic flux of these interstitial atoms. So let's take a look on here. These two terms is a chemical potential gradient and a temperature gradient. But however, the chemical potential gradient, in previous slide, you know, chemical potential gradient will be affected by what? Will be affected by the concentration and also the temperature gradient, temperature. So actually, chemical potential is a function of concentration of the interstitial atoms and also the temperature. So you need to divide these two parameters and rewrote the du chemical potential as this one. At constant temperature, then partial mu, partial c dci, and at constant concentration and partial mu, partial t dt separate into these two parameters in terms of the concentration and temperature. Then based on previous knowledge, you know what's the partial mu, partial c, this term. This is what we have from when we derive the Einstein relationship, right? We know the chemical potential gradient is linear with the concentration gradient. So you move this term to the left-handed side, you got will be kT over C1. Substitute this term. And the bottom part, what's the partial mu, partial t? Chemical potential of mu A at XA can be expressed like this, right? Pure chemical potential of A plus this composition term, and this composition term can be rewrote as a minus T SA bar. SA bar here is a partial atomic entropy here. So you partial this with a T, so you got the minus S1 bar is a partial atomic entropy of these interstitial atoms, right? So you use this term to substitute this chemical potential gradient, then you will get these results. And you successfully divided this chemical potential term into concentration gradient and also temperature gradient. Then you need to arrange them, put the temperature gradient together and concentration gradient together. So I believe I did something. So what you get after arrangement, the concentration gradient part can be equals to always the fixed first law always work, right? So the concentration gradient part will be always equals to minus diffusivity concentration gradient. And the second part will be related to temperature gradients. Then we can after arrangement or organize them, then we can simplify, arrange them as mobility, concentration, and driving force also. So how to do that? And the driving force here is a minus Q heat of transport, temperature gradient divided by T. Okay, we call this Q, we call it heat of transport, is equals to this term. So after combine these two terms and after arrangement, then you can have this simplified term, and probably you can try to do this. This term is this term, right? And I try to help you to organize this term. So the first term here is a diffusivity because of fixed first law. So we just and because this relationship we can get L11 equals to D1C1 over KT. And the second term is a temperature gradient term, is included this term and this term. We just copy them here and pull out the temperature gradient outside, and the D1C1 over KT. This is what is L11, right? And we take this term out and simplify as this term, right? Because you take the minus D1C1 KT squared, so this we times the minus T S1 bar. So times the minus is a positive, right? And TT, okay, so L1Q is over T, right? So we take this term out, so what we have is this term. So then we just use minus D1C1 KT squared, copy here, and the red stuff we call it is heat of transport and temperature gradient here. So we can successfully organize like here, the same with this one. And why we want to do this? Because easy to remember. The only reason is it helps you to easily remember. Why? Because in the end of lecture 1, the driving force for thermal gradient is minus a minus temperature gradient over T. And if your material is suffer by the mass transport under the temperature gradient, you just need to put the modified term, we call it a heat of transport, Q trans, and the Q trans is equals to this term. So it's just easy to remember, because you can take a look here. It's also diffusivity, I mean the fixed first law, and the second part is the temperature gradient. You also can just easily divide it into mobility, concentration. Driving force is a purple stuff. This Q heat of transport times the minus temperature gradient divided by T. So it's easy to remember. So based on this, you can how to measure the heat of transport. Yes, how to determine the heat of transport. Yes, in the beginning you have material and with a uniform concentration of interstitial atom, and then you apply a temperature gradient along this material. Then this as long as this gradient is larger enough, then this driving forces can going to push these interstitial atoms toward to right-handed side. So after a while, you can observe the profile of interstitial atoms becomes here like this. So you can expect more there's a driving force toward to right-handed side, right? And the concept will be as long as there's exist of concentration gradient, so the system or material itself is going to will arise the other driving force to try to counterbalance this atomic flux driven by temperature gradient, right? So the value will be minus diffusivity concentration gradient, trying to balance it. So as long as this two atomic flux, the value, the magnitude of this flux are the same, it can reach we call the Quincy steady state, and the Ji equals to 0. So at this moment, you can calculate the heat of transport will be expressed like this. And as we mentioned, the T is a working temperature, so you know that, right? And the concentration gradient will be, you can use the EPMA or SIMS to know the concentration profile of on your materials, and the temperature gradient is you apply on it, you know the temperature gradient is what. So it's easy to calculate the heat of transport of your material, right? So this is how we determine the heat of transport. But here, probably some people will consider one thing is, how about the direction of the temperature gradient you apply on the system? Based on these figures, we know the direction of concentration gradient or direction of temperature gradient, matter the sign of heat of transport. What's the relationship between this? So based on these results, I mean, this concentration profile, gradient, this is positive, right? So positive and negative, so the upper part is negative. So if the temperature gradient applied on this material is positive, so this is a positive, negative divided by positive, so the heat of transport will be negative. And what this tell you? The heat of transport is negative, and the atoms be pushed, the interstitial atoms be pushed from, it's go this way, right? So it's pushed from low temperature toward to high temperature. So it will be against the temperature gradient. So heat of transport, the sign of heat of transport tell you the direction of the moving species. In this case, is against, because the atom in the beginning they are the uniform, right? And after I apply this temperature gradient, then I observe the atom be pushed from low temperature toward to high temperature is against the temperature gradient. On the contrary, if the temperature gradient I apply on this material is like this way, it's a negative temperature gradient. So the upper part is the negative and negative, so the heat of transport is positive. And this tells you the atoms be pushed from high temperature toward to low temperature. So it's along the temperature gradient. So the sign of heat of transport tell you also the direction of the moving species be pushed due to the temperature gradient you apply on this system. So it's quite important. Okay? So every material have its own, every element or every diffusing species have its own heat of transport. As long as you you can use this way to get that, and this the sign of heat transport can tell you the direction of diffusing species under this temperature gradient you apply on the system. Okay, so today just ended here.